In this video, we're going to look at how to sketch exponential equations. We'll start by looking at how each term of the exponential impacts its shape, and then we'll finish up with an example of how to sketch them by hand. For those who don't know me, my name is Chris Ionazoni. I used to work as an engineer for a defence company, and I've since left that to start a career in tutoring. I make these videos so that VC students can do the best they can in math methods. With that out of the way, let's get into it. This is the general form of the exponential. Now, there's a lot of terms to keep track of there, so let's look at them all individually. There are two main scenarios when it comes to the base of your exponential. The first is if your base is greater than 1. Under these circumstances, your exponential is going to increase from left to right. We also observe that as x gets smaller, the y values get closer to 0. Let's look at why. First, why do the y values increase as x gets larger? Well, let's test a few. If I were to sub in x equals 1, I would get y equals 2. X equals 2 is going to give me y equals 4. X equals 3 is going to give me y equals 8. We can see that this trends upwards. Now let's see what happens when x gets smaller or more negative. 2 to the power of negative 1 is a half, 2 to the power of negative 2 is a quarter, and 2 to the power of negative 3 is an eighth. We can see that this trends downwards as the denominator gets larger, we get closer and closer to 0. Furthermore, if the base itself gets larger, then this effect is magnified. It'll rise faster for positive x values, and it'll fall faster for negative x values. The second possibility is if your base is between 0 and 1. Under these circumstances, we observe a reflection in the y-axis. Why? Well, once again, let's test some values. If x equals 1, then we have y equals a half. If x equals 2, then we have y equals a quarter, and so on. We see that the behaviour is flipped. Furthermore, if our base gets even closer to 0, then the effect is magnified once again, where it's going to rise faster for the negative x values and fall faster for the positive x values. The a term is a dilation factor from the x. It's responsible for stretching the graph vertically. If a gets larger, then it's going to get further away from the x-axis. If a gets smaller, or closer to 0, then it's going to get closer to the x-axis. The d term is similar to a, but it works in the opposite direction. If d gets larger, then we observe the graph to get closer to the x-axis. If d gets smaller, then we get further away from the x-axis. Just a reminder that d is a division. That means that x over 3 is a dilation factor of 3 from the y, whereas 3x is a dilation factor of a third from the y. Reflections are identified as a negative sign, either applied directly to the exponential or specifically on the x variable itself. Reflections about the x-axis are signified by the negative sign at the front of the exponential, and reflections about the y-axis are signified by the negative sign directly attached to the x. Just a reminder, the base can also cause a reflection, so there's actually two terms that are at play when it comes to determining what the reflection is of an exponential. Let's look at a few examples. If your base is greater than 1, then it normally rises from left to right. A reflection in the x will therefore mean that your graph is going to fall from left to right. If your base is between 0 and 1, then it normally rises from right to left. A reflection in the x will therefore cause it to fall from right to left instead. As before, if your base is greater than 1, then it's going to rise from left to right. A reflection in the y is going to flip that direction. It's now going to rise from right to left instead. And again, if your base is between 0 and 1, then it normally rises from right to left. A reflection in the y is again going to flip that, so that now it rises from left to right instead. The last thing we look at are the translation factors. These are responsible for shifting the graph either horizontally or vertically. Horizontal translations are determined by the h term. If you have x minus h, then you're shifting to the right by h. In this example, we have x minus 2, hence our graph is shifting to the right by 2. If you have x plus h, then you're shifting to the left. In this case, we have x plus 2, meaning that we're shifting our graph left by 2. Vertical translations are determined by the c term. If you have plus c, then your graph is shifting up by c. In this case, we have 2 to the power of x plus 1, hence our graph is shifting up by 1. If you have minus c, then your graph is shifting down. In this example, we have 2 to the power of x minus 1, hence the graph shifts down by 1. It's also worth noting that vertical translations are directly tied to the equation of the asymptote. So, when it comes to sketching exponentials, you need to know three things. You need to know the location of the asymptote, the axis intercepts, and if you have a restricted domain, you will also need to find the endpoints. We use the following framework when it comes to sketching any exponential. Let's try an example. To begin, we just want to make sure that we're starting with the general form of the exponential. This will allow us to figure out what all the key features are of the exponential much easier. In this case, we can start by distributing the multiplication of -3 through the brackets. We can then take this a step further by focusing on the exponent and taking the common factor of 2 off of the x. From here, we can easily identify the equation of our asymptote. It's just equivalent to the vertical translation, which in this case is y equals 1. Next, I recommend determining the shape of your graph ahead of time by looking at the reflection terms. In this case, we have a vertical translation up by 1 and a reflection in the x. So this means that our graph should fall from left to right. The reason why we do this is because we want to know ahead of time whether to even bother solving for x-intercepts. If the graph was trending upwards, then we wouldn't have any, so we don't even have to bother trying to find them. Speaking of axes-intercepts, let's find them. When it comes to solving the x-intercept, we're going to set y equals 0. This is going to require us to convert our exponential to an equivalent logarithm. For y-intercepts, we're just going to sub in x equals 0. This one's much easier to simplify. From here, we would try to go find any endpoints, but in this case there is no restriction on our domain, so we can happily move on to the next step, which is just to sketch our graph through those key features. One of the issues we run into here is trying to figure out whether or not our axes intercepts are positive or negative. At a glance, it can be quite difficult to figure out, are my terms positive or negative? My recommendation is to focus on the y-intercept. Anything with a negative index is just a fraction. Furthermore, we know that e is approximately 2.7, and 2.7 to the power of 6 is going to be quite a large denominator. So multiplying that by -3 is just going to cause you to have a very small negative number. When you add 1 to that, it just means your net result is going to be positive. From there, you don't even have to bother with the x-intercept, you already know that it's going to be positive, because otherwise the shape of the graph just wouldn't work out any other way. If there is a restriction on the domain, then you have to find the endpoint by subbing in the lower and upper bound into the original function. When you do that, you get the corresponding y values. Having achieved those coordinates, all you do is cut the graph off early at those spots. Just be mindful of the brackets. If you have a square bracket, then you have to use a full circle. If you have a rounded bracket, then you have to use an open circle instead. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.